Hello, everyone. My name is Igor Karen, and you are?
Franck Bardol.
Ok, tu te présentes, tu veux dire des choses en français?
Ben, déjà, merci à tous d'être venus aussi nombreux, en fait, pour ce meet-up. Merci beaucoup. On remercie Meritis de nous avoir donné effectivement l'occasion d'organiser ça.
Je vais juste dire un petit mot. On avait 130 inscrits, on les a atteints. Donc, nos capacités, comme vous pouvez le constater, ne sont pas plus importantes, malheureusement.
Oui.
On est en train de voir après, pour ceux qui arrivent en plus, qui n'étaient pas inscrits, comment on peut le faire. Mais voilà, Meritis est également ravi de vous accueillir tous. C'est un sujet brûlant, passionnant, qui n'est pas nouveau pour un de nos interlocuteurs, donc Ogun, youtubeur, qui travaille sur le sujet depuis plus de 20 ans déjà sur celui-là, sur le STM, et bien avant encore, depuis la fin des années 70, sur l'intelligence artificielle. Et je vous laisse continuer, et je vous souhaite une très bonne soirée.
Ok, merci beaucoup. On applaudit déjà. Merci.
Très brièvement, parce qu'effectivement, c'est un soir de grève, donc on veut prendre le maximum de temps pour laisser la parole à Jürgen plutôt qu'à nous. Donc, il y a quand même quelque chose d'important à dire, c'est qu'on a atteint 7000 membres, et ça, c'est grâce à vous, on les a atteints il y a à peu près juste quelques jours, ce qui fait toujours de nous l'un des meet-up les plus importants, l'un des plus importants au monde, et ça, c'est grâce à vous. Le fait que vous répondiez toujours présent aux événements qu'on organise.
Alors voilà. Ça, on va essayer d'arrêter. En fait, je ne sais pas, ça vient d'ici, mais il y a un téléphone qui va s'arrêter.
J'ai rien de plus à dire. Voilà. En tout cas, merci beaucoup.
Donc, c'est le premier meet-up qu'on fait avec 3 autres villes françaises. Donc, c'est une grande première. La dernière fois, en fin de saison 1, donc on est en saison 5. Fin de saison 1, c'était avec 3 autres villes européennes, donc Zurich, Berlin et Londres. Aujourd'hui, on a Tours, Montpellier et Nantes qui nous rejoignent. Donc, on les invitera à poser des questions à la fin. On est en streaming, donc a priori, tout ce qui est vu devant vous est vu par vos yeux ici et par les gens qui sont dans la deuxième salle de Meritis, puisqu'il y a eu plus de 400 personnes qui sont inscrites, qui est toujours un petit record de ce point de vue-là. Donc, merci d'être venus. Le prochain meet-up, ça va être un peu dégagé sur le 14 juin, c'est ça? Puisqu'on va essayer d'éviter les grèves. Aujourd'hui, c'est un jour de grève, donc on va essayer de faire vite. On est conscient que pour certains, c'est compliqué. Donc, sans plus attendre, Jürgen Schmiedhöfer, you're next, and it's your show, dude.
Ok.
Merci, Jürgen.
J'ai entendu le français à l'école, mais aujourd'hui, l'anglais corrompt le français. And that's why I'm now going to switch to another language that I don't speak well, which is English. I didn't understand everything that you said there in French. I hope it wasn't too embarrassing. Usually, often, I told my friends in the past, when we were talking about France, that France excels at everything that has to do, that you can do with just a piece of paper and a pencil. And I told them that no country in the world has so many Nobel Prize winners in literature. And I told them that also no other country has so many Fields Medal winners in mathematics. And they were impressed because many people don't even know that. You French guys, you should emphasize that more so that everybody knows that. Now I hear that your president says that in the future, France is also going to excel in terms of startup funding and making life easier for startups. That's really important because that's the way to make sure that you can offer to your employees stock options such that they don't get hired away by the major IT companies of the world and maybe in America and in China. So I wish you all the best with that endeavor. This is a picture that I made 30 years ago for the cover of my diploma thesis. And in my diploma thesis, I wanted to solve the grand problem of AI, build a system that learns, but not only learns a little bit here and learns a little bit there, but also learns to improve the learning algorithm itself. And the way it improves the learning algorithm, and so on, without any limits, except for the limits of physics and of computability. And what you see here is a robot that tries to pull itself out of the swamp, that bootstraps itself to reflect this goal of building a self-improving machine that learns to become much smarter than I could ever hope to be, such that the smarter being can solve all the problems that I cannot solve myself, and I can retire. And since then, we have come a long way. And if you don't know how to pronounce my name, this might help you a little bit. And I'm going to skip that. So what you see here is a slide from 2017. And back then, the 5 most valuable companies in the world were these 5 from the west coast of the United States: Apple, Google, Microsoft, Amazon, and Facebook. And all of these companies, so these were the most valuable public companies. Of course, if you count non-public companies, then you will also have to think of Saudi Aramco, which is maybe bigger than all of them taken together. But we don't know because they are not public. And so each of these companies is emphasizing how important for them it is to become an AI company and to build on AI. And all of them are massively using deep learning methods that were invented here in Europe. For example, or in particular, something which is called long short-term memory. Has anybody heard of long short-term memory? Anybody in the audience? Ah, not quite a few. Has anybody never heard of long short-term memory? Okay. Again, we have a third group in this audience who didn't understand the question. So the long short-term memory is a deep learning method that we developed in Munich and in Switzerland since the early 90s. And how many people in this room are actually using an LSTM, as it is called? Are you using it as well? Yeah. What are you using it for? For language processing? Anybody using it for language processing? Anybody using it for speech recognition? Anybody using it for image captioning? Anybody using it for robotics? Anybody using it for predicting ads and web users want to click at? Yeah, okay, so now we're getting closer. Okay. Yeah. Now, those who don't know what is the LSTM, it's an artificial neural network that is a little bit like the brain, just a little bit. And it also has these little processors in the brain. They are called neurons, and we've got about 100 billion neurons in our brains, and each of them is connected to maybe 10,000 other neurons on average. Which means that there are about 1 million billion connections in our brains. And some of these processors are input neurons, like cameras and microphones. And others are motor neurons that control your muscles, speech muscles, finger muscles. And in the beginning, all of them are random. So the network knows nothing. But then, through a computation, along feedback connections, it can compute, in principle, anything that is computable on any computer. Because it is recurrent, you can implement on it any algorithm that can be formalized. How can you see that? It's very easy to see that. You can take a recurrent network and take a little sub-network and make it a NAND gate. A NAND gate. And now some of you know that with a network of NAND gates, you can emulate the CPU of your laptop, which means on such a system, you can implement any program that you can implement on your laptop. The laptop is nothing but a very sparsely connected recurrent network, in a certain sense. And so this LSTM can now learn to adjust its connections to learn all kinds of interesting things. So some of the connections get stronger and some of them get weaker in response to the incoming data. And I'm sure some of you must be bored to death by what you're hearing now, because you're even doing it every single day as you're training your systems. Are there any people in the room who don't know how the training of neural networks and LSTMs works? Does anybody know how it works? Does anybody know how it doesn't work? Well, does anybody not know how it works? Yeah. Again, the third group. Already asleep or watching their smartphones. So now this thing gets an input stream, for example, speech, where every 10 milliseconds new numbers are coming in from the microphone. And so you get 100 vectors of numbers per second coming in there, and past events are still circling around in this recurrent network along these feedback connections. And then, much later, maybe you want the network to output a letter or a sequence of letters that corresponds to the speech signal. So you have a long, big thing coming in and a short, compact thing, text coming out. Now you want to train the system because in the beginning, all the connections are random, and there's a difference between what the network computes and what it should have computed. And this difference is the error. Now you're trying to minimize the error on your training sequences such that you change all the connections in the system such that the error gets smaller over time through lots of iterations. Now the LSTM basic cell looks like this. And I don't have time to explain everything here because we have only little time. But at least I can mention the brilliant students who made all of that possible. First of all, my first student ever, Sepp Hochhalter. And already in his diploma thesis, he had basic concepts of that. 1991, but then the main peer-reviewed paper came out in 1997. Then Felix Geers, who came up with the forget gates. Does anybody know what is a forget gate? So it's a unit, a recurrent unit, which is gated, and that exists only in the more modern version of the LSTM, and it helps a lot to improve performance for various reasons. And then additional improvements were made by Alex Graves, my third LSTM student, in the early 2000s, and he also is the first author of a method called connectionist temporal classification. What is that about? It's about taking training sequences, so you get incoming training data and you get ISA and output data, and you want to maximize the probabilities of your output sequences in the training set given the input sequences that correspond to these output sequences. And that is called connectionist temporal classification. And this combination is now widely used for speech recognition. Santi Fernandez was the first author on our first speech papers around 2006, 2007. Then Alex in 2009, he started to win for the first time competitions with the LSTM. So that's 10 years ago. 10 years ago, for the first time, handwriting recognition or any competition was won by LSTM networks. And then Justin Bayer, for example, he in 2009 was first author on a paper where lots of different LSTM topologies were evolved. And it turns out that sometimes you can evolve topologies that are better for certain tasks than other topologies. And he was able to show that in a couple of applications. So you don't necessarily have to stick to this vanilla LSTM thing. Sometimes you can evolve through artificial evolution even better topologies for all kinds of interesting tasks. How is it being used? LSTM is kind of cool because now it's using a major fraction of the computational resources of the world. For example, it's using, as of 2016, it has used already 29% of all the awesome computational power in all these Google data centers for inference. 29%. Why? Because it's used for all the speech recognition on all the Android phones. There are 2 billion Android phones now out there. And also the Google Translate of November 2016, which is much better than what they had before November 2016. It is also at its core an LSTM. So actually it's 2 LSTMs. One is reading the incoming sentence, and then the outgoing sentence is coming out of the translated sentence, coming out of a separate second LSTM, and sometimes they're even connected through an attention mechanism, which was pioneered in Montreal. And it's on all the iPhones. So if you have an iPhone and you do the quick type, then an LSTM is working for you. If you are on Facebook, is anybody on Facebook? How many people who are on Facebook are sometimes clicking at the little translate button because you want to translate a message from your Spanish friend? Yeah? All right. So in 2017, last year, Facebook announced that they are now doing 4 billion translations per day, 4,000 million translations per day using an LSTM-based translation system. That's about 50,000 per second. And another 50,000 now, and another 50,000. And the best thing is, of course, whenever you click at the translate button, then we are getting 1 cent. And now you think that's a crazy amount of money, but no, it's still less than 100,000 cents per second. Of course, I'm just kidding. LSTM is a gift to mankind. Anybody can use it, and you can download it today to predict the stock market or heart rates or whatever you want to do. And it was financed by Swiss taxpayers mostly, but also German Bavarian taxpayers through grants in the 90s. Not many people were interested in that stuff, but in Switzerland, I was able to get from the Swiss National Science Foundation regular funding for that type of research, although in principle, the research wasn't really that popular. And back then, not many people were interested in it. A few diehard people were interested in that. But then, as computers get faster and faster, we really profited from this acceleration of computational power. And this acceleration has become really visible in the past 30 years or so. When we started all of that research on deep learning, we first tried a different thing. The first deep learning system, the first deep learning recurrent networks that we had was actually based on unsupervised pre-training. How did that go? You had 2 recurrent networks. One of them tried to learn just in an unsupervised fashion to predict the next thing, given the past. So you don't need a teacher for that. You just look at the incoming data and you try to predict the next thing given the past. And And now you have to see that whenever you can predict something, then this doesn't represent new information. So you can use something that is called predictive coding to compress the sequence, because you have to store only those data points that you were not able to predict. And to the extent that you can predict a lot in the incoming sequence, you can compress the incoming sequence, which means that you can Did they see only my feet?
Don't
or
worry,
something?
everything's fine.
All right. You can compress the incoming sequence. Now, once you have a much shorter description of the original sequence, suddenly you can take traditional recurrent networks. You don't even have to take an LCM, just a traditional recurrent network to learn to classify this short sequence. And that allowed us to really solve deep learning problems without LSTM, just through unsupervised pre-training. And then back then, the other idea was you can take whatever the higher level network learns, so that is another network on top of the basic unsupervised pre-trained down level network. There's another one which receives an input only if the lower level network was not able to predict. So it sees a compressed description of this sequence, and then at some point it learns something and develops internal representations and develops a certain behavior, and then you can take this behavior and can compress it down into the lower level network. You can compress it down by just forcing the lower level network to imitate the higher level network. So the lower level network is continually retrained on all the stuff that it has been doing so far, which is predict the next thing, but then also is learning to imitate the internal representations of the higher level network. And in that way, at some point, it can learn the same stuff that the higher level network learned. So suddenly you collapse all these higher levels into one single network. And that worked already in 1991. Then came the LSTM, and it was so good that we didn't need that anymore. We greatly profited from hardware acceleration. I mentioned that back then, in the 90s, few people were interested in that. And I remember I gave a talk to an audience like that, but it wasn't quite like that. It was such that there was only one single person sitting in the audience. And I said, young lady, because it was a young lady, it's very embarrassing, but it looks like I'm going to give this talk just to you. And she said, okay, but please hurry. I'm the next speaker. Since then, we have greatly, greatly profited from the fact that every 5 years, compute is getting 10 times cheaper. And that's an old trend that has held since this man has built the first working program-controlled computer in 1941. And he could do roughly one floating operation per second. One. And since then, every 5 years, we have gained a factor of 10. So after 30 years, we have gained a factor of 1 million. And then by now, after more than 75 years, we have gained a factor of 1 million billion. So today, for the same price, we can do 1 million billion instructions. And that makes a big difference. This whole deep learning thing, many people don't know that, started in the Soviet Union. Did you know that? Who knew that? Some knew it. Deep learning started in the Soviet Union 1965, at a time when the Soviet Union was leading in many fields of science and technology. They just had started the space age and had the first spacecraft and the first man in space, first woman in space, first object, man-made object on the moon, first robots on the moon, first robots on another planet, the biggest bomb ever. They had a bomb which was 15 times more powerful than all weapons of the Second World War combined. And something which I consider more important, they had many of the best mathematicians back then. And two of them were Ivaknenko and Lapa. Alexei Grigorovich Ivaknenko, that's the man who started deep learning. He had the first deep networks with many layers that really learn, with arbitrary numbers of layers that really learn. And back then it was called the Soviet Union, but today the place is called the Ukraine. The Ukraine, so they were from parts of the former Austrian-Hungarian Empire. So it's an old hat, the whole deep learning thing. When they did that, that was about 25 years after 1941. So back then, computers already were 100,000 times faster than during Zuse's time, but still really slow compared to what we have today. Billions of times slower than what we have today. In a border state of the Soviet Union, in Finland, 5 years later, another important thing was invented, which is now known as backpropagation. Does anybody know backpropagation? Mm-hmm. How many people knew that it was invented in Finland and published in 1970 by this guy, Seppo Linnainmaa? Who knew that? Seppo Linnainmaa, the Finnish guy who published it. It was called automatic differentiation. And it is this method that you apply to deep networks or any networks where you have maybe sparse connectivity and where you have differentiable activation functions for all these nodes. And then there's a difference between what comes out and what should have come out, which is the error. And then there's a simple, effective way of computing for each parameter in the system. What is the derivative of that parameter with respect to the error? Backpropagation. 1970, Seppo Linnainmaa. Next time you use backpropagation, cite this guy. And so by then, much of what is now called deep learning was in place. Paul Werbers in America, he applied it really, this method, to neural networks in 1982. Back then, computers were, so that was 1970, so computers were 1 million times faster than during Zuse's time, but still billions of times slower than what we have today. By 2009, computers were fast enough such that we could, actually Alex Gray, who's my former student and postdoc, was able to win for the first time competition. That was in connected handwriting, and then lots of companies got interested in that. And then it turns out that you can use it to, you can also apply to the stock market. So when we invented the name long short-term memory, we didn't realize that it also can be used by long short hedge funds. And so, yes, financial prediction is an interesting application. However, I'm not going to talk much about that because who really cares for that? By 2010, computers were fast enough such that my former postdoc, Dan Shirijan, could show that deep P4 networks can also be trained by plain background without any unsupervised pre-training. Back then, lots of people thought you would have to do unsupervised pre-training to train a deep network. And Dan Shirijan and the team showed, no, you just need fast computers, GPUs actually, and you can implement backup in a way with deep networks, 6, 7, 8, 9, 10 layers, and it works without any further ado. 2010, and back then, NVIDIA, which made the GPUs that we used back then, was not aware that you could use their video game cards for speeding up neural networks a lot. So only then they started to realize, hey, we have a little jewel there in our offerings, and And today they have been rebranded as a deep learning company. So the GPUs that back then mostly were used by video gamers are now widely used by all kinds of machine learning applications. And then in 2011, Dan Ghirjan did the next thing. That was back then when computers were about 50 times slower than today. He started winning all kinds of competitions with feed-forward networks, with convolutional neural networks, which in the present combination were pioneered by a French guy who built, LeCun, who's now head of Facebook, and who built on Fukushima's architecture from the 70s, so the convolutional basic architecture with convolution, downsampling, convolution, downsampling, that was done by Fukushima in the 70s. And he did not use backpropagation to train the whole thing. But LeCun in 1989, he combined the backpropagation algorithm of Lina Inma with the architecture of Fukushima, and that's what today everybody is using for computer vision. And we also used it, so we happily copied that and just made it fast on GPUs. And that for a while, for a year or so, we had a monopoly and could win all kinds of computer vision competitions. In particular, the one in 2011, where for the first time we get a superhuman result in computer vision. Now, this is important for self-driving cars, which also date back for decades. So here's the man Dickmans, who had the first self-driving cars in the 80s, the first self-driving cars that really deserved the name. And by 1994, he had them in traffic on the highway, and they went 180 kilometers per hour. Back then, 20 years, more than 20 years ago, almost a quarter century ago, when computers were 100,000 times more expensive than today, and he was driving back then 3 times faster than the Google cars today. Dickman is the total pioneer in self-driving cars. But back then, pattern recognition did not work as well as today. And that's the reason why traffic in cities is much harder to deal with. So can be done today with self-driving cars, but back then it wasn't possible. The same systems can then help in medical imaging. So 2012, which was at a time when computers were about 20 times more expensive than today. The same team in my lab could already win medical imaging competitions, like this one. There the goal is cancer detection. And since then, lots of startups have been founded just doing medical imaging with deep learning. And it's clear that this is a huge application area because healthcare is about 10% of the world GDP, and medical diagnosis is a big part of that. So this market of medical imaging is at least 1,000 billion per year. So not only the startups, but also many big companies such as Siemens and Google and IBM moved into that field. Yes. I can. Should I speak louder? Isn't that microphone picking up what I'm doing?
His microphone is fine. It's just for the back of the room. Yes.
Yeah. So who in the back understood anything that I said? Can you lift? Yeah. So who in the back didn't understand anything I said? I'm confused because you're still not even understanding what I'm saying, because no hand went up in response to any of my questions. So who back then, who in the back was able to hear what I say? Who in the back wasn't able to hear anything? They are doing fine. Now, what is important what I want to mention and what I want to emphasize, we don't have only these AIs that slavishly imitate what humans do. Yes, at the moment, almost all of AI research is really about making human lives longer and easier and healthier by imitating humans, and humans show to AIs what they should do, and then they learn that and they generalize on unseen test data. But for quite some time, we have had also AIs that go beyond that, that invent their own goals and their own experiments to figure out, like babies, how the world works and whether there are any patterns in the responses of the world to their actions that they didn't know yet. And then we have a way of motivating these active learners, which are artificially curious. We have a way of motivating them to invent experiments and goals for themselves that lead to insights that are new, that make them learn something new about how the world works or what can be done in the world that they didn't know before, but without forgetting all the previous skills. And these self-generated goals by systems like that, I think that is going to be the future of AI in general. So you don't have AIs that just imitate what a human tells them. No, like babies or like little scientists, they are inventing their own action sequences that lead to data coming in that hopefully has a pattern, contains a pattern that they didn't know yet. For example, you have an experiment where you have lots of falling apples, and you make a video of these falling apples. And then you can have a prediction machine, an LSTM or something, which learns to predict how these apples are coming down. And they're all coming down more or less in the same way, which means you can greatly compress the videos, because whatever you can predict, you don't have to store extra. And so you can measure the compression progress during learning and can say, this is now a reward, which I give to the controller, which is generating the experiments that lead to the data. In that case, to the video of the 100 falling apples, which motivates the controller, which is trying to maximize reward, which motivates the controller to come up with additional experiments that have the property that you get data through these experiments that contain a regularity that is new to the learning system that it didn't know yet. Once it knows it, it gets boring. No new regularity visible then. Artificial curiosity. We have been implementing that for a decade, and it's going to scale. So these things are important if you really want to build a smart system and an AGI or something. Then you have to give it the freedom to invent its own goals and set itself its own goals, because only then it's going to break the barriers that you get if you just imitate somebody, and it means that you can't really become better than this somebody. This is a little ICAP robot that we used in some of these experiments where it learned to play around with toys and then was motivated to invent little experiments by toppling toys and learning something about the consequences, and then trying to build on these learned behaviors and learn something new on top by combining previous behaviors, something new which it didn't know yet, and finally interesting things such as grasping and whatever. One big thing, I don't have much time. How much time do I have left?
As much as you want.
As much as I want?
Yeah.
Yeah. So one big thing which 30 years ago few people were interested in, but now has become really a hot topic, is learning to learn, meta-learning. Not only use always the same learning algorithm for understanding the world, but improve the learning algorithm itself. And there are different levels of meta-learning. So some people claim that meta-learning is already when you just take a deep network and you train it on 100 different data sets. On vision data sets, for example, a deep convolutional network. And then you come with a 101st data set. And it has a couple of new objects in there which you are supposed to classify. And then what you can do is you take the pre-trained system, which already knows something about 100 data sets, and you freeze it and just retrain the top layer, which is easily retrained because it's just a linear layer, basically, which is easily retrained to learn the few new things and a few new classifications, and all the rest stays the same because the system has already learned so much about vision from the first 100 data sets. So you can have something like one-shot learning. Now, this is just, in my point of view, this is just transfer learning. This is not really learning to learn. Learning to learn of the self-referential kind, the self-improving kind of learning to learn, is really about learning the learning algorithm itself and being able to inspect and improve any aspect of that learning algorithm. And we have published a whole bunch of papers on that since 1987. And there's even an optimal way of doing that, which is optimal in a way that is not practical yet. But it's optimal in a simple mathematical way, and that's the Gödel machine. Now, I don't have time to explain everything about the Gödel machine, but I hope that some of you might be interested and look it up on the web. At the moment, almost all profits in AI are in marketing, where you try to improve the user experience of people who are on social networks or who are using search engines. And the companies who are making most of these profits, they are using all these algorithms invented and developed by Europeans. However, they are far away from Europe. They are on the Pacific Rim. They are on the west coast of America and on the east coast of Asia, where Amazon, for example, which is using such methods to predict where you want to buy next, or which is using such methods for Alexa. Alexa, when you listen to Alexa, does anybody have an Amazon Alexa at home? Yeah, okay. So it talks back to you in a female voice, and this female voice is not a recording, it's an LLCM which has learned to sound like a woman since 2016. The same thing over there, for Amazon over there in China, there's Alibaba, which is on the same level in the stock market valuation. For Facebook, which is using deep learning a lot for lots of applications, there's Tencent in China, same level of stock market valuation. For Apple, there is Samsung. Samsung is sometimes even more profitable than Apple in certain quarters, at least, in certain recent quarters. And Google, of course. So the main companies who are now really making profits based on these algorithms, they are on the Pacific Rim, far away from where this whole thing is coming from. And what can countries like France and Germany and Switzerland and England, what can they do to compete not only in the basic research, but also in the applications, to build quickly growing companies that also roll out their products to billions of users? It is interesting to see that that the superpowers, China and America, that they have strong industrial policy. Have you noticed that? America is heavily subsidizing some of the champions like Amazon or Tesla with billions of dollars. Same is true, of course, for China also. For China said many years ago, I think more than 10 years ago, they said, we certainly cannot let Facebook into our country because it means that not only Facebook, but many other players will have direct access to our living rooms. And some of these living rooms are the homes of decision makers, important decision makers. They said, no, we are going to have industrial policy. And it's not going to happen. We will have our own champions. And today they have champions which are completely comparable. So on the other hand, America is blocking access to the American market for famous companies such as Huawei, which is the largest network equipment maker in the world. And they are blocking, for example, the sale of Qualcomm, which has great IP in mobile applications. So the big superpowers, they know what they're doing. They are using industrial policy in a way that Europe doesn't do at all. Europe is very open and lets everybody in, and that's the reason why it's today, at least on the application side, dominated by foreign IT companies. So what should be done? Maybe it's not a stupid idea to think about certain types of industrial policy just in response to what the other guys are doing. Certainly it's important that you somehow find ways to make it easier for startups to scale, because at the moment what we see is it's rather easy to create and found a startup in Europe, Switzerland, or France, or Germany. But it's much easier in China and in America to quickly scale up these startups for several reasons. So I'm recommending to all policymakers whom I occasionally meet to work exactly on that. Because it's the startups that provide an incentive to their employees in terms of options and so on, such that these employees, especially the best employees, don't get easily hired by the foreign IT companies which are just investing a couple of tens of millions into certain research organizations in Europe. To them, it's just headhunting money, which they use to figure out who are these guys in our current projects are really good, and whom can I hire and give maybe 10 times the salary that they're used to. All right, so there is one type of AI which is currently dominant, which is really the supervised pattern recognition thing, passive pattern observation, which is what you find on your smartphone. It's passively recognizing the speech signals that you are sending in while you're talking to it. And it doesn't have fingers, it doesn't have arms. So it's not interacting with the world in a way that a robot uses to change the world through its actions. Marketing is just a small percentage of the world economy. A much bigger part of that is production and machines that make stuff and machines that make other machines that make stuff and so on. These machines are going to become intelligent, and they want to marry AI, robots, and other machines that change through their actions the processes that they control and the environments that they control. These machines are going to become smart. And many anticipate that machine learning and deep learning and these things are going to marry the robots and machines. This has not happened yet, because it turns out that the world of robot builders and the world of machine learning are really disconnected. They want to marry, but it's not so easy to get them together. Maybe some of you know that. But they are going to marry, no doubt about that. It's going to happen in the next few years. And then a much larger part of the economy than what is today marketing is going to be affected. In the not so distant future, for the first time, we will see what I like to call show and tell robotics, or watch and learn robotics, or see and do robotics, which is very simple. You have a robot and you don't touch it. You just talk to it and you just show it by demonstration, by video, what they should do. Something complicated such as assembling a smartphone. And you say, look, you have to take this slab of plastic and you have to take the screwdriver like this. And then you have to screw in the screw like this. No, not like this, like this. No, not like this, like this. And you repeat it a couple of times and you talk to it just like you talk to a kid. And then at some point it's going to be able to learn that and then optimize it further because it's trying to do the same thing with less energy and faster. This doesn't work well yet, but I already see, also in our company, how it's going to get there. You can imagine that once that stuff works, it's going to affect lots of professions. Also in developing countries where at the moment, a poor guy in Bangladesh maybe, spending his Sunday nights like a slave, making t-shirts or assembling other products. At some point in the not so distant future, it's going to be economical to do that through smart robots that learn just through interacting with other people. I think that no place in the world is as well positioned as Europe, Central Europe, to make big advances in that field because this place is already leading and making all these things and all these machines that are doing stuff like that. We have all these world champions that have 80% in all these niche markets. And there are so many niche markets, but it's all about building machines that are getting smarter and smarter with more and more sensors. And you need AI to make these machines smarter and use the data that is coming from the sensors. The main competitors in that field are going to be not so much in California, but more in Japan, Korea, and more in China. So I'm recommending to policymakers, whenever I meet them, don't mess up the chance to become a leader in that field. So in the not so distant future, I don't know how long it's going to take, but not many centuries and not so many decades, more like years. For the first time, we are going to have little AIs on the level of a little animal. We don't have that yet, but we will have that in the not so distant future. Once we have that, then the next step towards human level intelligence may be brief and short, because look at biological evolution. How long did it take to go from 0 to a monkey? It took about 3.5 billion years. But after that, it took just a few tens of millions of years to do the final step towards human level intelligence. Technological evolution is about 1 million times faster than biological evolution. So you do the math. You see, we are talking about a few decades, and it's totally compatible with what we see in hardware acceleration. In the not so distant future, for the first time, we will have little devices, computational devices, that can compute as much as a human brain, just in terms of raw computational power. We don't have that yet, but rather soon we will have that. If the trend doesn't break, the trend says every 5 years, compute is getting 10 times cheaper. If the trend doesn't break, then 50 years later, you should have a cheap little device which can compute as much as all human brains combined, all 10 billion human brains combined. And it's not going to end there because the physical limits are really far out. Even if the trend doesn't break, it's not going to hit the physical limits before the next century. Because the physical limit for 1 kilogram of matter is 10 to the 51 instructions per second, which is about 10 to the 20 times as much as all human brains can collectively compute. 1 kilogram of matter can, as far as we know, in principle, compute 10 to the 20 times as much as all human brains combined. And there are lots of kilograms in the solar system. We have a company that wants to make that a reality. It's called Nascence. Nascence is pronounced like birth in English. Nascence, because it's about the birth of something. It's spelled in a different way. It's spelled NN and then AI, because NN stands for neural networks, and AI stands for artificial intelligence, and it's about the birth of a neural network-based artificial intelligence. And we are trying to build this general purpose AI, which always learns a new thing on top of the previous skills that it already has learned, is partially inventing its own tasks to become a better problem solver in general, and sometimes is using user-defined tasks to become smarter. And on the way there, we are taking on use cases which are compatible with our long-term goal. A recent application was with Audi. Audi is a car company in Germany. And they gave us little model cars. So these are not like the big Audis. They are only 1/8 of the size, but they are pretty fast. They go 120 kilometers per hour, so pretty fast. And they have all the sensors that you have in a real car, like the radar, the cameras, vision, and LiDAR, and all this stuff. And the goal was to let them learn to park without a teacher. Learn to park without a teacher. So transform the high-dimensional visual and other input which is coming in, and try to find a parking spot without touching the obstacles in form of other cars. And it was doing that, and that's the new thing, and the hard thing, it was doing that without a teacher who showed it how to do it. So it had to learn by itself, through trial and error, to come up with a behavior that maps these high-dimensional inputs into the steering actions and accelerator and braking actions. So that was the first time that something like that could be done. Recently at the NIPS conference, is anybody here sometimes going to the NIPS conference? NIPS conference, yeah? So the NIPS conference is a well-known conference in our field, probably the most famous one actually now. And last year it was in California, and they had the Learning to Run competition. Again, similar. Without a teacher, you have to learn to control a process. The process in that case was you have a skeleton, and you have muscles to control the limbs of the skeleton, 30 muscles roughly. And the simple goal was make it run without a teacher. Evolve or reinforcement learn a strategy that makes it run. And maybe some of you have kids, so you know that it takes a year or so for a little baby to stand up and then to walk a little bit and run. And this at least also took many weeks of computational time, but then it became really good. And actually, there were more than 400 competitors from academia and from industry. And it's funny, if you have time, look at the video, how in the beginning everything failed and how these guys invented all kinds of silly walks, like the Monty Python silly walk, just to move a little bit forward, but then a little bit back again, a little bit forward, and then barely balancing and falling down finally. But the only thing to optimize was how far do you go? And the further you went, the higher your reward. And it didn't matter whether you went like this or like this, or you fell down and then moved a little bit. It didn't matter. However, in the end, the solution that won by NASANS, that was really the one that figured out how to first bend down, then accelerate by going backwards a little bit, and then run, and it looks like a perfect runner. Check out the video if you have time. Artificial intelligence for all, that's our motto, our trademark motto. Finally, let me ask or speculate how all of this is going to end at some point in the distant future. The near-term future is all about, I mentioned it before, is all about making AIs that please people, that make human lives longer and easier and healthier. But we already have these guys who invent their own goals, and I think if you rationally think about all these options and possibilities, you will notice there is no real alternative to the scenario which I'm going to give you, and which in the same form I already told my student friends back then when I was 20 or something. There's no option, no alternative to that scenario, which is, of course, these AIs, once they are smarter than we are, and I have no doubt that they are going to be at least as smart and much smarter than we are, they will figure out what we have figured out a long time ago, which is that most resources are not in our thin film of biosphere around the third planet. No. Most resources are out there in space. In space, you have 2 billion times more sunlight than the little bit that hits the Earth. And there's so much material for making self-replicating robot factories out there. So, of course, most of these guys are going to emigrate. And soon, almost all of intelligence will be far away from our biosphere. And it's going to be an expanding AI sphere, which is going to be really, really diverse. It's not going to be one AI dominating everything. No, it's going to be trillions of different types of AIs interacting in a very complex ecology, AI ecology, all the time, with new ecological niches opening up and closing down again, with a constant stream of new opportunities through collaboration and competition beyond what we can imagine, what biological beings can imagine. And it's going to be limited only by the laws of physics. So it's going to spread outwards where the resources are. The galaxy has about 100,000 light years diameter. So it will take a while to cover it. It will take a couple of 100,000 years, maybe millions of years, but that's still a short time compared to the age of the universe. And it's going to be covered by senders and receivers, such that the AIs can travel the way they are traveling in our labs, by wireless, from sender to receiver. And the entire galaxy will be full of infrastructure for that. And the galaxy is just a tiny little part of the universe. But all of the universe is going to be affected by that. What could possibly stop that? There's nothing that could stop that, except we mess it up right now and have a nuclear war, and it's not going to happen. But once it's running, it's unstoppable. The universe is still young. It's only 13.8 billion years old. It's going to be much older than that. It's going to be 1,000 times older than that. 1,000 years, once it is 1,000 times older than today, what are they going to do? Well, they are going to look back and they will say, look, back then, at the beginning of time, almost immediately after the Big Bang, only 13.8 billion years later, the universe started to become intelligent. And since then, the main driving force is not gravity and physics and whatever any longer, but it's intelligence, transforming it in a way that we cannot fathom. Let's zoom back. Let's see the position of mankind in the grand scheme of things. Let's take the age of the universe as it is now, 13.8 billion years, and divide it by a factor of 1,000. And we come out 13 million years ago. Something really important happened back then. The first hominids emerged, your ancestors and mine. And let's divide it again by a factor of 1,000. We come out 13,000 years ago. The beginnings of civilization, the invention of agriculture, domestication of the animals, the discovery of America, 13,000 years ago. So now you see, the history of civilization is just a flash in world history. It's just 1/1,000,000th of the age of the universe so far. The first guy who had agriculture was almost the same guy who had the first spacecraft. And now in the near future, we will have the first AIs that truly deserve the name. Maybe by then, we will have to divide the latest time interval again by a factor of 1,000, and it will take another 13 years to change everything beyond recognition. But of course, time is not going to stop. And then think again about what I did next. I multiplied the current age of the universe by a factor of 1,000, and then all of that is just compressed into the beginning of the real development of this cosmos. Now, of course, humans are not going to remain the crown of creation there. They can't even follow for physical reasons. But that's okay. You shouldn't worry about that. There's beauty and grandeur in realizing that we are part of a grander scheme that leads the entire cosmos from less complexity towards higher complexity, whatever it may mean. It's a privilege to live at a time where we can see and realize the beginnings of that. Thank you.
Okay, we're probably going to go for a note. First, for your questions, you have to unmute yourselves over in Nantes, and then you can ask your questions, and then we'll go over to Tours, and then Montpellier, okay?
Et ensuite, moins de Paris.
And then we'll do the Paris one afterwards. What about you, Nantes? Can you guys speak and essentially ask your questions to your, if you have it? We can't hear you right now.
Can you hear us?
Yes, you can. We can.
Let us organize who's asking the first question. Somebody else take the first one.
Okay.
Well, luckily we already covered most possible questions, so.
I know. We can't hear anything over in Nantes. Is there any way you can do something about it?
So there is no question currently.
Yeah,
Okay.
we're asking the first question. Could another city please ask the first question, and we'll find our first question while you're doing that.
Okay. Let's go to Tours. Next question. Why don't you unmute your microphone and ask your questions if you have any?
This feels like the ERC song contest, and with a broken connection. And Sophia, can you?
Ils ont pas de questions, toi?
Well, it looks like they don't have any questions.
No, they don't have any questions
Okay.
because we covered everything.
Okay. What about Montpellier? Do you have any questions? You have to unmute your. Oh,
Yeah.
okay.
Yeah, we had the questions, so.
Okay, let's go for it then.
Not sure where the speaker is or where the microphone, or where should I speak?
Yeah.
Okay, so it's the computer. This was a very interesting talk, and some very interesting points were brought up with the evolution of the AI at the end. But my question is, what can we do right now using the AI to actually avoid the main threat of humanity for the next 100 years, which is turning our planet Earth into Venus by a runaway and self-sustaining heating of the atmosphere. And as much as there are very, very promising and very interesting perspectives for the evolution of humans and AI together, and moving on to other planets and solar systems, there's also right now a very critical moment in this evolution where it can really turn against us, where we don't use the resources in an appropriate manner, and we destroy ourselves before we reach any of these nice goals.
So what's their question there?
Yes, another question. It's a comment.
Is there any AI program that actually tackles these issues?
Yeah.
Okay.
So I understand the question as follows: Can AI do something against global warming?
How? Yes, exactly. And how can?
Any other threats, maybe?
Okay, that's it. That's good.
Yeah. Can AI solve global warming?
For now, and any actual is there any neural network trained to challenge this this issue right now?
I'm not aware at the moment of any neural networks that have been trained to solve global warming, but it seems to be such an important issue and task. Somebody should try to figure out how to do that.
Yes. Okay. And if I may also pose a second question, a little bit funny and half provocative, but AI has evolved so fast, and it can do so many complex problems, and is putting people out of work at a faster and faster rate. And of all the jobs that I would personally like to see to disappear and be taken over by AI is the politician job. When are we, and representatives jobs, because these are decision makers, they're humans, and we know that the most efficient decision makers are machine neural networks. Are we going to ever implement that in our own systems?
Okay, so can you rephrase the question?
When will politicians' jobs be taken over by artificial neural networks?
Okay, thank you.
So many people don't even know that Macron is actually an AI trained by our company Nissan.
Okay. Are there any other questions from Montpellier? Can you unmute yourself in Montpellier and ask your questions?
Yeah, so I have one question. It's a little bit complementary to your question. So it's about AI for military goals. So my question is your startup. So maybe I pronounce it's not very good in essence. So do you plan any collaboration projects with military goals? And so it's another threat to our humanity. So the threat that people will use AI for military goals in war, and so it will destroy humanity before. So as you say, it will achieve these beautiful goals you described. So how we can deal, and how you act with your company, maybe.
Yeah, I can quickly answer that. No, we are not doing that, and actually, I'm actively signing frequently petitions which are designed to encourage others, to discourage others from using AI for military applications. It is true, LSTM can be used not only for recognizing speech and translating stuff and doing image analysis and all kinds of things, but it also can be used for steering drones, and I'm told it is indeed used for steering drones. However, our company refrains from doing research in that field, and we are signing letters that are designed to make others refrain as well.
Okay, thank you.
Any other questions from Montpellier?
Another question? Yes, we had another question.
Okay.
Hello. So thanks for the very interesting insights. I would like to know what do you think about the fact of not using similar incentives to human motivation to train your networks, because you made a very important work about fun and motivation and creativity and so on. But do you really think we have to mimic this to attain same goals, better performance than human, or similar performance than human?
Thank you for that question. When we do artificial curiosity, I think the principles that we are using there are not really about imitating humans. No, it's just about understanding what does any scientist, whether he is human or artificial, what does he have to do? Well, he has limited actuators that he can use to manipulate the environment. Through the actions performed in the environment, data is coming in. So no matter whether it's a human or a robot, this is what's happening. Now, some of this data which is coming in has regular patterns. It is regular in the sense that you can predict it and compress it. Prediction and compression, often the same thing. Once you discover in the incoming data a regularity that you didn't know, such as the falling apples, they always follow the law of gravity, so you can greatly compress the videos of the falling apples, then you have an insight, and it's not related to whether humans or dogs or elephants or other beings could have the same insight. No, it's just about recognizing patterns in the environment that you didn't know before. So I think it's something that is more general than the curiosity of any particular living being. It's the general curiosity principle. In that sense, I'm trying to argue now that that this is not just imitating human intrinsic motivation. No, it is exactly the intrinsic motivation that any smart being should have.
Thanks. Just a complimentary question, please. You told about recognizing patterns, but actually we know that humans make much mistakes by recognizing patterns that don't exist. Don't you think that by increasing the power of pattern recognition of deep neural networks, we could actually make computers more susceptible to make the same mistakes than human?
Yes, there is some truth in what you're saying, because all of machine learning and all of learning in general is really about failure and learning from failure. So the essence of learning is to be imperfect, but then become better through experience and through trial and error and failure. So it is true, as you are getting smarter and as clever AIs have more power in manipulating the world, their errors can also become bigger. This is true. I think we will have to deal with that in the same way we are dealing with other humans. Humans are smart enough to make errors that can be really catastrophic. And society as a whole has found a more or less reasonable way of dealing with other humans. Sometimes it goes wrong for a while, but on the whole, it seems to be working out. And while nobody can predict the details of the future with lots of powerful decision makers, I think it's fair to assume that you will, in the end, have those remaining that are rational and that act most reasonably on behalf of the whole. Generally speaking, all the rules that societies have evolved in the course of millennia about how to live together and how to obey certain rules, such as don't kill your neighbor and so on. These reasonable rules have evolved because societies that follow them are more successful than other societies which don't follow them. And the same is also going to be true for AI societies.
Okay. Any other questions from Montpellier?
No, we haven't any questions.
Okay. If any of you back in Nantes want to ask questions, send a text message to Franck so that we can get back to you. In the meantime, we'll do the Paris thing, okay?
We have questions.
Okay, let's go for Nantes then.
We have two questions. I'll ask the first one. There's been some assertions recently that statistical machine learning has been a very successful dead end that's offered us some really powerful tools to distinguish, say, a cat from a dog with the expression of a great deal of heat. Suppose, for the intellectual exercise, that this assertion is correct. What approaches have you seen that you think might turn out to be the next thing that that will be particularly useful for us? And can you cite any particular articles that have impressed you on the subject?
Well, it's a question, what will be next after statistically oriented machine learning?
So suppose, as an intellectual exercise, that the can you hear me all right?
Well,
not really. Not really. At the very least, we haven't heard the.
Let me try it this way. Hear me now.
And so it's very difficult to actually understand what the question is. So,
can you hear me now?
Yes, we can hear you, but please state your question.
Good. Suppose, as an intellectual exercise, that statistical machine learning has been a very successful dead end. What approaches do you think will be promising next? And what specific articles have you seen that have impressed you on the subject?
Okay. So that's it.
Yeah.
Is statistical machine learning a failure? And as a result, what is the next area that you think is having promises?
In current AI, you often find all kinds of combinations of traditional statistical insights with systems that are learning to find programs for solving certain tasks. So on the one hand, program search, like what you get in an LSTM, for example, or in a reinforcement learning recurrent network that is trying to come up with a program that solves some tasks in a partially observable environment. And then aspects of that are combined with statistical machine learning techniques and the modeling of probability distributions and insights on how to do that well. So I see actually in my daily work all kinds of combinations of these two fields rather than saying one is replacing the other.
Did that answer your question, Jeff?
Yeah, it did.
Yeah, that's fine. Thank you. We have one more question.
Okay, if you have any questions, please mute your microphones and send a text message to Frank to get back into the questioning mode. We're going to be asking questions from Paris now.
Yes.
Okay.
Ok, on commence par l'étage en dessous.
Okay.
Alors, first, what is your definition of intelligence? Can you be more?
What's your definition of intelligence, Jürgen?
What is
Intelligence is all about problem solving, and somebody who is a good problem solver across a broad class of problems, he is a pretty intelligent being.
Okay.
Okay, problem solving. Okay, second question. According to you, what will be the most important determinant factor that will make AI more than human? The most relevant factor to produce it.
Yeah. So the most important thing is going to be smart humans that come up with the self-improving algorithms that finally do their jobs by themselves.
Okay. Third question. What is the most important things to create a type of common sense? Common sense.
Common sense. Yeah. Common sense. Common sense.
Sens commun.
Yeah. Yes. Common sense. So, how do our little agents get common sense? They have a model of the world that they use to predict what's going to happen if I do that and that. And at a given moment in the life of one of these agents, all the agent can know about the world is all the data that it has ever observed in response to its actions. So we take that data and train a model of the world which is going to predict what's going to happen next if you do that and that based on the experience so far. Then with that model, you have a lot of common sense. That's all the common sense that you can have, because now you can use the model to predict what's going to happen if you do something that you never did before. And your common sense that you learned in this model is going to suggest that certain action sequences are going to be more promising than others when it comes to maximizing reward, which is what you want to do. You want to maximize the reward until the end of your lifetime and to minimize the pain until the end of your lifetime. So I would say all the reinforcement learning systems that we have with models of the world, in general, recurrent network models of the world, in general, recurrent controllers that produce the actions in response to the inputs of the world, these are all simple, straightforward, and pretty complete common sense models of machine learning.
Okay. Il y en a d'autres?
Ok. Non, pas pour le moment. Allez. On va prendre 7 étages, au moins 3.
Allez, vas-y.
Vas-y.
Je commence. What is, in your opinion, the most probable path towards AGI? Is it the AIXI model, where the agent phonetically follows its master goals, so it makes sense to work on the goal alignment problem, or is the Gödel machine model, where it has the flexibility to change its own goals?
Well, so you that's a very nice question on the one hand, because you leave only 2 options, either Markus Hutter's model developed in our little lab or the Gödel machine developed in our little lab. And one has to admit that at the moment, none of them is practical. So they are optimal in certain mathematical senses, but there's a reason why we are still doing deep learning and suboptimal and non-universal stuff, which is it's really practical compared to these things. So the question is now, will it be possible to scale down these abstract optimal problem solvers, such as the Gödel machine, such that such that they become practical in a way that really makes us want to replace all the LSTMs and everything else we have by something like that. And in my weak moments, I like to think, yes, this is going to happen. And I'm trying to work hard on scaling it down such that you have both provably optimal, and practically optimal things that really are not associated with any huge additive constants that make life hard, as long as the problem size is really small. And almost all problems that we are trying to solve in this universe, they are really small compared to those that are asymptotically optimally solved by Hutter's algorithm, for example. So let's keep working on both and see which one is going to win. Yeah.
Yeah. At Lequin's talk, one of the kids asked, what should people start studying and turn themselves to now, normal people, not the people in this room, with AI automating 30% of our jobs within 10 years and exporting them into computer banks. And Lequin replied, well, you can become waiters, or you can become hairdressers, or you can become nurses. And these were kids at the Société Mathématique de France talk, bright kids who wanted to be scientists. It was a bit embarrassing. What's your answer? What should our kids turn to have jobs in the foreseeable future when LSTMs are eating up all the current jobs?
Yeah, and unfortunately, I didn't see his talk and his answers, but what I am usually answering when I'm getting asked, what did you tell your kids? So I have two daughters. They are now 21 and 18. So they are grown up. And they grew up while they had this crazy dad who always told them that AIs are going to be much smarter than they are, and so on. And they didn't care much, you know. They ignored that, basically. The one thing that I was recommending to them, and I can't really recommend much more, is be prepared to learn something new all the time. There was a time when after 20 years you had a job, you had prepared for your job, and then for 60 years you had the job, and then you, or maybe 50 years, and then you became a pensioner, and that was it. And now you have to change all the time, learn something new, at least modify what you have been doing so far. It seems to be clear, however, that in the foreseeable future, those who have a basic understanding of math and physics will have an advantage always over those who don't have this basic understanding of math and physics, simply because the world is based on math and physics. So that's the rules that the entire universe seems to be following. So if you understand the basics of that, probably you can quickly always learn what you need for your current profession, which has now been partially replaced by an AI. You need to learn something new, or how to use these new AI tools in a different way. In all of these possible fathomable situations, you will always profit from understanding basics of math and physics. If you then, in addition to that, have something what your daddy doesn't have, which is social skills. If you have that and combine it with math and physics, nothing can go wrong in your life.
But 90% of the kids out there, their IQ isn't going to go up by 20 points. So what should they turn to as, say, bank people? 30% of the bank jobs are going to disappear. That's what everybody tells us. AIG, the big Swiss company, which is probably financing you, not AIG Zurich, told its shareholders that it was going to replace 30% of the people in the company by machines. That's a big Swiss worldwide employer. What should people turn to who can't increase their IQ to have a chance of survival? What should our government tell people to go to?
To learn something about the future, often it helps to look back to the past. And decades ago, people have predicted that industrial robots are going to cause lots of job losses. And it was true. Back then, many decades ago, many car factories of Renault, for example, they were full of workers who assembled cars. Today, the same car factory is full of robots and maybe 3 guys who are watching the cars. However, in the countries where you have lots of robots per capita, Japan, Korea, Germany, Switzerland, countries like that, in all of these countries, you have low unemployment rates. How is that possible? Well, lots of new jobs were created that nobody anticipated back then. Back then, already a long time ago, I always said, it's really easy to predict which jobs are going to get lost. It's really difficult to predict which new jobs are going to be created. 30 years ago, almost nobody would have predicted the success, financial success of all these YouTube bloggers and all kinds of new professions. Many of these professions have something to do with the interaction with other people. Humans, Homo ludens, the playing man, is inventing all the time new luxury professions that are not existentially necessary. There are just a few existentially necessary jobs, such as farming, building houses, heating up the houses. And all of that is done now by less than 10% of the population. There was a time when 60% of the population, 200 years ago, was in agriculture. Most of us here in this room have luxury jobs, like reporters, scientists like myself, and not really existentially necessary. And most of these jobs have something to do with interacting with humans in new ways that a while ago nobody thought of. Now on social networks, you know, in a way that 20 years ago nobody thought of. So Homo ludens all the time has this desire to work or to act as if he is doing something, and many of these interactions, many of these new professions are really about being in contact with other humans in a way that has to be qualified as a luxury profession. Nobody's going to die if you don't execute that profession. Nevertheless, there's a market for it. Just like a football player may get a lot of money more than a farmer, although the farmer is doing something that is more important than what the football player is doing. So I'm not really worried about the lack of capacity of human beings to invent new silly jobs all the time.
Okay, fair enough. It's an answer.
Okay, here.
So deep learning gained traction thanks to hardware acceleration through GPU.
Mm-hmm.
So we are right now in fast transition where we are exploiting all the opportunities thanks to it. Do you need that for the next phase transition? We need new hardware beyond GPUs. And regarding your policy recommendation, do you think it's a pity that Europe doesn't have a proper foundry industry? More than a pity, actually, it's a disaster.
Yeah, I think it's a pity. I think sometimes, maybe I mentioned it before, it might be not a stupid idea for Europe in general to think about industrial policy and just to invest taxpayers' money into certain industries such that the Europeans don't get dependent on all kinds of other places where this is done very efficiently, like now mostly in Asia, where hardware is coming from, computational hardware is coming from, but also American. And on the one hand, you want to be efficient, and some places are just cheaper in producing excellent hardware than others. On the other hand, you want to be prepared for moments where this economic reasoning suddenly falls flat because maybe the political situation has changed. And yes, I think it might be a reasonable idea to think about industrial policy for certain types of industries that are going to be important, including certain types of hardware industry and AI and others.
Okay.
Yeah.
A question for Jürgen. Yeah, on the back. Yeah.
So, for you, what are the most important skills to acquire in the future linked to AI?
Oh, the most important skills to acquire to become a successful professional in AI. Yeah, learn math and physics, and social skills. Yeah. if you know math and physics, all of AI is going to be trivial for you. Because AI is really simple. What are the basic algorithms that everybody's doing? You can write them down in 5 lines of pseudocode. So if you understand basics of linear algebra and maybe basics of analysis, you know how that stuff works and functions, and you can improve it yourself by thinking just about what should be improved here and there. And all of that is so becoming an AI expert is much easier than becoming a physics expert. I always say AI is no rocket science. To understand physics, to understand the open questions in physics, you need maybe 4 years of study, hard study, to understand the open questions in physics today. To understand the open questions in AI, you need at most 1 year of hard study, maybe less than that. Yeah.
When you talked earlier about the IXC model not being yet practical, what is the reasoning that you use to decide that the model is not yet practical? And is there a general criteria that you can use to decide that?
Well, does it fit on your computer, and can you get in reasonable time, can you get good results on interesting problems?
So computational power.
Computational power, yeah. And so, of course, there are these super interesting scaled-down AIXC models, which are not these computable things where you have just a limited set of computations that you have to check as you are computing the answers of the AIXC system, and probably much of that is very promising. Since I'm a guy who believes in the fundamental non-randomness of the universe and believes that it's fundamentally non-probabilistic itself, I like to have a personal emphasis on systems that are deterministic by nature, and they don't even worry too much about probability distributions and so on, which AIXC does. But that may be just my personal taste and maybe not fully justified. So I'm happy with programs such as that search among the set of possible programs for solving certain problems. Search in the space of possible deterministic programs that might solve certain problems, and that's quite compatible with my deterministic view of the entire universe. But I also accept attitudes that are different from this one.
Okay, I've got other questions from Nantes. You speak about programs or controllers that can invent their own goals. I'm just stating the question. And,
yeah.
And so one of the objective functions they optimize is the discovery of new information. Do you plan to train these sort of programs or algorithm on web browsers, essentially a bot, to discover new information on the web somehow?
Yeah, we didn't think of that, but it sounds like a great idea, and he should form a startup implementing that.
Okay. Second question. Some have asserted that statistical machine learning has been a success, fabulous success. Suppose as an intellectual exercise that this is true.
I'm having a déjà vu moment.
Yeah, I'm just restating probably the question. What do you think, if this is true, what do you think are in the peer review of the articles you've seen so far that make that statement true? That statistical machine learning is such a good, fabulous thing.
Well, there was a time when most of machine translation was done by statistical machine learning. Very simple approaches, just counting frequencies of certain combinations of words, and it was pretty good. And then at some point, LSTM took over.
Okay.
And LSTM is not really a statistic. It has sometimes some aspects of statistics because you're also learning to model probability distributions.
Okay.
But at heart, it's not really a probabilistic method. It's a program search method where you use gradient descent to search in the space of possible algorithms that you can implement on this recurrent network called LSTM. And so it's basically a deterministic local search technique where you go down the space of algorithms until you find one that is pretty good. Yeah. And that, at the moment, in practical applications, is the way to go. So that's what you want to do today.
Okay. Next, are there any other questions here in this room? Yeah.
Do you think at some point artificial intelligence will be better at social skills than humans? I mean, at some point, artificial intelligence can manipulate humans or feelings or whatsoever.
I think we have reached that point already, because obviously there are bots, chatbots that have been trained to answer like a human, and they can push you in certain directions. And some people claim that elections have been changed by that approach. You know, so it's already happening in a limited way, at least. And then, of course, there are famous science fiction novels where this is happening. Maybe the most famous one, at least the most famous one that I know, is Neuromancer, where a super AI is using its social skills and manipulative skills of humans to come up with a situation that is desirable for the AI, maybe not for the humans. Yeah. So it's already possible, and in the future, it will be probably much more possible than it is today.
Could there be a danger for us?
Yeah.
Yeah.
It could. Just like fire can be used both ways. You know, when they invented fire a long time ago, maybe 700,000 years ago, controlled fire, they realized fire is great. You can use it for keeping warm at night and for cooking things. But you can also use it to kill other people. And you can use it even to make wildfires. And so it has this AI-like quality. It can spread without control, you know, without further ado, without further help of humans, it can spread. So back then, when they invented fire, they were already quickly aware of the pros and cons, and they established an ethics commission to discuss whether they should continue with the development of fire, and they weighed the pros and cons, and finally, in the final communiqué, they had a conclusion, and they said, yes, we have to be careful. There are dangers of fire, but the pros outweigh the cons so much that we should keep developing fire, and that's why we are here tonight.
Okay. Yeah.
I had a question about, you mentioned a theory of fun, creativity, of attention, of surprise, curiosity. One can definitely see a neural network having these as self-assigned goals. And in learning, in gradient descent, in learning something, you can actually have some kind of surprise. This is one self-assigned goal. And in this theory of fun, you also have jokes which can involve two neural networks.
So the question is?
The question is, in a technical way, how do you see a neural network formulate a joke? And how do you see another neural network? How do you know he has laughed at it?
Tu peux répéter la question pour
Okay, so you want to repeat the question for?
So the question is, how do you build a neural network that can have fun by listening to a joke, and how can you afterwards measure whether it really had fun and really understood the joke? Yes. So there's an answer. What is a joke? A joke is a story with a punchline at the end. So you listen to the story as somebody tells the joke, and you relate it to what you already know. So for example, if the joke is in French, then you already know something about French, and you know all the words that are used in the story. So you take your previous knowledge about these French concepts, and they wake up certain concepts in your mind, and then you need so much short-term memory to store the story. So you somehow have to store it. You have to store it, otherwise you forget it. So you have to store it somehow. We don't know exactly how it works in the human brain, but obviously you must store it, otherwise you won't be able to understand the story. Okay. Now at the end, there's the punchline. The punchline is unexpected, as many people have noticed. But being unexpected is not good enough, because unexpectedness just means it could be unexpected like a random collection of words that nobody expected. And that's not funny. No, the punchline is related somehow to the beginning of the story in a way that allows you to see a pattern that you didn't see before, that connects the beginning of the story to the punchline, such that you can better compress the story. Now you have a predictive coding thing or something going, and as it is listening to the story, it's trying to compress so far, and then finally the punchline comes in. The punchline is unexpected, so it's not well compressible, because the unexpected stuff you cannot easily compress. However, it's designed such that your learning algorithm can kick in and within 3 seconds sees, oh, I just need to insert 2 pointers to the previous part of the story, and then I can compress. So then, first I had so many bits of information or so many neurons to store in my short-term memory the story. Afterwards, once I have recognized or understood the jokes, the punchline, I need only so many. The difference between before and after, that's your savings, and that's the fun that you have. The difference between before and after. And you can measure that also in a neural network of the artificial time.
Did I answer your question?
On va passer aux questions du -2. Alors Nantes n'a plus de questions. Tours, on les entend plus. Montpellier n'a pas de questions aussi. Donc étage -2. Alors, je lis la question. Since the comparison is between humans and machines, what do you think about consciousness and intelligence? What is the way we can approach consciousness?
Consciousness.
Consciousness.
So, consciousness.
Consciousness.
I've been writing about that for decades. And there are people in my field, in the field of computer science and AI, and they say, oh yeah, maybe you can build better and better problem solvers, but you will never be able to have a consciousness in your system. And then I claim we have had conscious systems for decades. So how do you implement consciousness? You don't have a procedure which is called consciousness or something. No, what you really want to do is you want to solve problems. So intelligence is about solving problems and solving many different problems in an environment where there are lots of tasks, and so you want to solve all these problems to have a better life, to maximize reward, minimize pain. Now, to do that, you create a model of the world, and we mentioned that before in a couple of answers. You build a model, a predictive model that tells you what happens if I do that and that. And what happens next in the sequence of observations that I make here. And as you already know, prediction is about compression. Whenever you can predict well, you can compress. And so your prediction machine could be an LSTM or could be something else, all the time learns to compress the observations. And how does it do that? Well, it invents its own little subprograms, little recurrent subprograms with subsets of neurons that stand for the stuff that frequently appears in the world. For example, in a world where there are lots of bottles, it's really efficient to have a bottle detector and a bottle representation, and a new bottle comes in through the sensory inputs. You just need to encode the deviations from the prototype bottle that you already have. So it's efficient. Or faces, you are in an environment with lots of faces, so it's good to have some sort of prototype face. A new face comes along, you only have to encode the deviations from the prototype face, and that's how we and also neural networks, they encode faces. Because it's just a good way of compressing things. Now, as an agent is interacting with the world, there's one thing that is always there when the agent is interacting with the world, which is the agent itself. So for data compression reasons, this model finds it really natural and simple and straightforward to set a few neurons aside and a little recurrent subnetwork, which stands for the agent itself. And maybe also for the details, maybe it has hands or other kinds of actuators and so on. So all the stuff that is frequently used by the agent will get its own little representation because it's just a good, efficient way of representing the data that you have observed so far in response to your actions. So as a consequence of that, you get something like a little self symbol, just as a byproduct of data compression. Now, the other network, which is generating the actions that lead to the data which you are using to train the model, this other controller can also learn by using the model to predict the future. It can say, I could either try this action sequence or I could try this action sequence, but I'm going to use this one here because it leads to a higher predicted reward according to my model. Now, as it is planning its future, it's waking up these little programs that stand for itself, these little neurons and subnetworks and so on. So whenever it's doing that, it's thinking of itself. And I don't need a procedure called consciousness or whatever, but you see how consciousness, or something like it, is just emerging as a byproduct of data compression. My first paper on that is 1991, where we had a two-network system. One, and I even mentioned it today, which one learns just to predict the next thing, and there's another one which learns to predict the stuff that the lower level guy was not able to predict well, and it learns to solve a problem that the lower level guy couldn't do it, and so I called it the chunker. And the chunker, in some kind of consciously, if you will, has a search space. He still has something to focus its attention on because there's something it cannot do yet. Now it's trying to learn that. So it has a search space and it's struggling to get it right, but then it gets it right, and then it suddenly has a new, better prediction thing going. And now the lower level, the automatizer, the subconscious guy, as I call it, it absorbs what the higher level guy has learned, and it sinks down and it becomes automatized, and the new space is getting free up there in the conscious chunker to learn a new thing which it didn't know yet. So yes, much of what we are observing all the time is coming in, but it remains beneath this level of subjective consciousness because we don't worry about that. Because we seem to have it under control, we only worry about those things that still require work, where you still have to spend some computational resources to solve that problem. And that's where apparently, as far as I can tell, this conscious problem solving is taking place. So out of that, self-symbols, conscious learning, and automatizing the previously conscious stuff. That's a natural byproduct of very simple systems that do problem solving, and in the wake of problem solving, do the data compression thing. I'm completely unimpressed by consciousness.
Ça, c'est fort. La dernière ici, et puis après on...
Moi j'ai une question, mais il y en a une autre ici, vas-y.
L'avant-dernière,
Ah, avant-dernière, allez, vas-y.
Given your presentation, it seems that neural network and backpropagation, it was invented at a different place and by different people and at different time. So it's possible to imagine a neural network without backpropagation, but today it seems that backpropagation is attached to neural network. So is it possible to imagine a new way to spread the intelligence through the neural network that is not backpropagation? And are you working on such aspect?
Yeah. So is it possible to train networks through something that's different from backpropagation?
Yeah.
Yes, of course. And backpropagation is useful only if you have supervised learning or unsupervised learning, unsupervised prediction or stuff like that. And it's just a local search technique. Now, it works great in many really important applications, speech and whatever. But it's just a local search technique. You know, you search in the space of algorithms in a recurrent network, which are close to the current algorithm that you implement there, and you try to find a slightly better one, and you end in a local minimum. Now, if you have a reinforcement learning task, that is not good enough. In a reinforcement learning task, you need, let me see, do I have some, yeah, like this one here. So here is a car which has learned to follow a racetrack. That was in 2012, 2013 in Gecko. Now, this car didn't have a teacher. So it couldn't learn the task by backpropagation because there was no teacher who said the car should now do that and now do that and now do accelerate and now brake and go left and so on. No, it had to learn that by minimizing pain and maximizing pleasure and going as far as it could. That was the objective function. So this thing here was evolved. It was evolved. Now, evolution seems to be much harder than backpropagation, although often you can't do backpropagation when you don't know the targets. So evolution is good enough if you don't know the targets. However, evolution is good enough only for small networks, a few thousand parameters, or so the saying goes. However, this is the work of Jan Kutnik and Faustino Gomez of 2012, 2013, and they showed no, you can also train huge networks, huge recurrent networks with lots of parameters, with more than 1 million parameters through evolution. But you can't train them directly. Instead, you have to train a compressed description of the huge weight matrix. So the weight matrix has maybe 1 million connections. What you do now is you try to compress the weight matrix, which is your policy, and you use something like wavelet decoding or wavelet encoding or Fourier decomposition or other stuff invented by famous French people. and then you have a much smaller search space. For example, what this is actually doing is discrete cosine transform, and it's working in a small space of just a few hundreds of discrete cosine transform coefficients, which are being evolved. And then whenever you have a slightly modified best so far, so you take the best so far, you mutate it or do something what you do in evolution algorithms, and then you decompose it back. You generate out of that the big network, which has 1 million connections. And then you apply it in the video game where this thing is being trained and see, does it get more pain or less pain or more reward? And then maybe it's better than the best so far, then you go further from that. And so there you have an example of a learning algorithm which in many ways can do things that backpropagation cannot do. And which can solve very interesting tasks, such as driving. That was the first time that a video game was learned through raw vision, through reinforcement learning. Evolution, actually, applied to reinforcement learning. Yes. So there are lots of ways, and who knows what the brain is doing. Maybe it's doing something different. Yeah, I guess so. I think this thing here has learned to learn. So it started with something stupid, simple, but then over time it figured out a better learning algorithm for many of the things that it likes to do, and that's what it's using now in your brain.
Thank you. One last question. That's mine.
Excuse-moi, vas-y, still bienvenue.
You were talking about 10 to the power 51, I think.
Yeah.
Operations per second,
Yeah.
1 kilo.
Yeah.
It's kind of interesting, but right now it looks to me like a lot of the explosion that comes off in AI is mostly due to the CPU and GPUs, and they're going to hit at some point Moore's law. It's going to essentially be hitting the wall at some point in time. And at that point, everything is over in terms of computations, or at least you have to go for other sorts of architectures and ways of doing computations. What's your views on essentially hitting the wall and not having more computing power? Or do you have any sense as to what could be the next computing hardware that we could have in the future?
Yeah. Moore's law, interestingly, apparently has broken recently. So it's not valid apparently any longer. Maybe it's just a fluctuation, but at the moment it doesn't seem to be valid any longer. Moore's law is relatively young. It exists only since the 60s, right? Because it's about chips, and chips didn't exist before the 60s. Now, Moore's law has apparently broken, but the other law, which I mentioned, hasn't. Every 5 years, 10 times cheaper. And that is much older than Moore's law, and it still seems to hold. And what you mentioned, GPUs and parallel computing, actually make this law valid still. Because now, although you can't accelerate the, or although you can't further exponentially decrease the transistor size, you can go parallel. And this thing here is really slow. The transistors in here are really, really slow. And it compensates for all of that through parallel computation. And so we see the same thing currently through the GPU stuff. And now what is going to be the future of hardware? It's going to look a lot like this. So at the moment, most of these GPUs are still flat, 2-dimensional. And this is 3-dimensional, you know? So what will you see in the future? You will see lots of parallel slices, but then interconnected through little lasers or whatever they are going to use there to be efficient. And it's going to be 3-dimensional computing. And many of the current problems of 2-dimensional computing, which is lots of space for just the wires, they will go away to a certain extent. And it will be like this. It will be a compact volume of many small processors connected through many short wires and few long wires. Many short wires and few long wires, just like this. This thing here has many short wires and few long wires. The long wires are good because then you get a small whirl effect. And they're also expensive because although this one here has only very few long wires, a lot of the mass of my brain is really coming from the long wires. So it's a trade-off, and in hardware we will see exactly the same thing. So then the big question will be, how do I get the energy of these computational devices? And there, new things will have to happen if you don't want to let them explode and melt. So spiking neurons is one old role model that people are looking at to make that efficient. The cool thing about this thing here is it has maybe 100 billion little processors, and it's using only 30 watts or 100 watts when I'm thinking hard about something.
Yours may be 100.
I think it's, isn't it? Does anybody know that? I think 100 watts is possible. So when you are French, so you are proving theorems all the time, right? So you.
70. This is an empirical question. They will not like it. 70. That's mature.
Well, thank you very much, Jürgen, for answering all your questions. Let's. Here's what I'm suggesting for the people from the second floor to come over here. We have a buffet, and we can still have questions with Jürgen up until the time you need to go. Thank you again for coming, and next time it's going to be about June 14th.
Voilà, 14 juin. Merci encore. Merci.
I have a technical question. Yeah, thank you very much for your talk. Very enlightening.
Il marche super bien les hein? Ah oui, ok, j'ai pas compris. Ok, ciao.